go. The doorbell is quiet. Give it a second. It knows when I start talking. Okay, so be it. Let me move the thingy out of the way here. So I have just the 2 questions here for formative assessment number 6. You should have gotten an email from me yesterday that homework 5 has been graded. A few of you have submitted revisions already, which I think sets some kind of record, so good work on that. If you wish to submit a revision to homework 5, you may do so before the end of finals week. If you have any questions on what you need to change, please don't hesitate to reach out. Sometimes my comments are not always clear, particularly when I have to grade so many papers back to back. I may adopt a shorthand that is less than useful. So if you don't know what you need to do, please ask. I'm happy to clarify. And grades have been updated as of just a few hours ago. So you all should know where you stand. So we have then 2 questions here about higher order factor models. Let me make sure the chat window is open, since that way I can eagerly await your responses. So what is necessary in order for the fit of a higher order factor model to be testable? What do you all think about this one? What do we need? At least 4 factors, yeah. So 3 for it to be identified without further constraints, and 4 for it to be testable. And what is the procedure for testing it? Not many people answered this question, so maybe I was not clear in what I was looking for. So if you want to know if the factors that you're working with are consistent with a higher order factor, how would you do a test to find that out? What do you compare it to?
Isn't this the saturated?
Saturated how? Because there's different levels of saturation, right? Up to this point, we talked about a saturated measurement model where all the indicators get their own means, variances, and covariances. But what do you mean by saturated?
Well, I think it was when we were talking about like the general one, and then the one after that we have to fix a factor variance to 1. So I thought I meant the first one where it's not fixed and everything's freeloading.
Right idea, wrong words. Not freeloading.
Free to vary. The loadings are free to vary. Is that right?
That would not be the saturated model if you have loadings.
Okay.
Do you want to phone a friend?
Yeah.
Okay, call on somebody.
Oh, wow. I'm sorry, whoever I pick.
And unless anyone wants to volunteer, but you've got the right idea.
Andrea, you might know.
Oh, calling her out.
No. Okay, so I'm thinking the same way you are, Kayla. But are you thinking, Lisa, about the factor variances, like allowing those to be freely estimated so that we can then compare them, which is like the
Not quite
testing?
closer, not quite the right word. Not factor
Okay.
variances. 2 more letters.
Covariances?
Covariances, yeah. So it's a saturated structural model specifically, where all the factors that you have in your model get to be freely correlated with each other. So all the variances are perfectly reproduced because they each get their own variance or disturbance. All of the covariances are perfectly reproduced because they're estimated directly. They don't have means that we're worrying about. And so that's as good as it gets. That's your baseline for what the best model could be, the answer key. Then you can compare your higher order factor model to it. And if you want to have a higher order factor, what are you hoping happens in that comparison? Do you want it to be significant or not? If you want a higher order factor. Not significant. Yeah. So you want to be able to say that your model with a higher order factor in it accurately reproduces the covariances among the factors. That's what you want to be able to say. And that is evidenced by a fit that is not worse. So this is another not worse. It's a weird thing to think about, but if it's adequate, then the model predicted factor covariances from the higher order factor model should match those from the saturated structural model. It's not enough just to show that you have good fit, because the measurement model is going to swamp all of the tests of fit. That's where most of the degrees of freedom are. So it's this comparison of what is the best structural model you can have is one in which everything is directly estimated, and then your comparison is relative to that. And it's only once you have four lower order factors that this is testable with 2 degrees of freedom left over. Yes. Does any of this story change if I have an IRT model versus a CFA model? Not really. The only catch would be if you are using regular marginal maximum likelihood, be prepared to wait, because for every factor that you introduce, at least in Mplus as a default, there's 15 points of integration. So with 2 factors, that's 225. With 3 factors, that is 725. And I can't do the math after that on the top of my head, but it's a lot. So if you're using full information maximum likelihood to estimate your IRT IFA model, be prepared to wait. If you are switching to WLSMV, then it will run more quickly, I should say. The only catch is that model comparison should be done using diff test. There is no likelihood out of those models. But otherwise, it's the same, because at that level of the structural model, the factors or the thetas or whatever you want to call them are multivariate normal variables. So the link functions that you worry about in the measurement model have nothing to do with the test of a higher order factor. Good. Questions on any of that? All right. Number 2, method factors or specific factors or bifactors, whatever you want to call it. What is the purpose of sticking these things in a model in addition to the general factor for what you thought you were measuring? What are method factors, specific factors, bifactors, etc.? What are they for? Taking what would have been residual or error covariance and putting them into the model as factors instead? Yes, exactly. So they represent the idea that there are additional reasons why your indicators are related beyond what you thought. And so putting them in as a factor allows you to have those additional relationships, but have a little more control over how to interpret them. So ideally, for instance, if you had some items that were worded positively and some items that were worded negatively, you might have a positive wording specific or method factor and a negative factor. And if you were able to constrain the loadings onto those specific factors to be equal across items, that would strengthen the interpretation that really all they have in common is the way they're worded. Because if they're all positively worded, like why would some items be more positively worded than others? Right? Like that doesn't make any sense. So you can control the interpretation by putting in patterns of constraints. So it's called a random intercept factor if all of the loadings are held equal to each other, by the way. They don't have to be one, just equal to each other. And oftentimes that can be used to save parameters or to strengthen interpretation. If you wanted to have error covariances instead, could you do that? If 2 items, say, have an additional relationship, could you put an error covariance there? Always? So this is where IRT versus CFA does matter. In CFA land, you can always put in a residual covariance, or you can do a method factor. In IRT land, it depends on estimator. So Jordan says, how about WLSMV? In WLSMV, you can have error covariances. You can, because remember, WLSMV, limited information estimation available for items that are treated as categorical, means that it is starting by estimating a polychoric correlation matrix. So it's polychoric for ordinal, tetrachoric for binary. And so you're back to a matrix again. So if there is a discrepancy in a particular pair of items, what the covariance should be relative to what it thinks it is in the data, meaning the starting matrix, you just plug that hole with a residual covariance and it's fine. If you are instead fitting an IRT IFA model and using full information, maximum likelihood, residual variances aren't parameters in that model. It's 3.29 if you're in logit land, or it's 1 if you're in probit land. Or ogive, by the way, IRT people, probit is ogive. So then you can't have residual covariances because you don't have residual variances. What you can do instead, though, are method factors. And that's why the term bifactor model, that originated out of the IRT literature as a workaround to the fact that you can't have residual covariances. It sounds cooler when you put it that way, but either way, when you have these additional factors or you have these additional residual covariances, it's a representation that says there's something else here in common besides the factor. So it's factor and stuff. Whatever is not the factor has some patterning to it. Good. All right. Any questions on that? All right. Then how about homework 6? Fun with invariance. Any questions on that so far?
I have a question
Sure.
about the what we're trying to do to do with the it's question 72. Which of the following will be true about absolute model fit in subsequent tests of invariance? I think it's just the wording with like larger versus smaller and them being like negative numbers. I just wanted to make sure I was understanding that right. Especially because also, did someone ask about this last time? Maybe I didn't know about it yet, so I was not listening good
Not
enough.
this question, I don't think.
Okay, good. Can we just talk about exactly what that means? So, for example, like if I add a constraint, that means that the model is going to fit worse, but I want it to fit non-significantly worse. And because it fits worse, the log likelihood is going to go up, which I think means larger. I'm not sure.
Yes. Yeah,
Okay.
it doesn't matter what the values are. So if you're on the negative side of the numbers, then a number that is more negative is a smaller number, and a number that is less negative is a larger number.
Less negative is larger. Okay. Okay.
Yeah, that doesn't change.
And even though I'm not trying to make the model fit worse, the chi-square is still going to get larger probably.
The worst or the smallest change is no change. Like it could stay exactly the same or it could get worse, but it's never going to get better.
Yes. Yeah.
Yeah. By taking things out of the model is going to fit worse or not worse.
Okay.
The exception to that is if you're judging fit by RMSEA, which is a parsimony corrected index, in which case RMSEA can actually get better, smaller, after you make the model simpler, but not in terms of log likelihood and thus chi-square.
Gotcha.
Yeah,
Thank you.
So this one, I like this one. This makes my head hurt just to look at it, but it's like, okay. Log likelihood, do you remember the theme song for maximum likelihood? I didn't get to sing it for you in person this year, but I put it in the chat window. It's Skilo. I wish I was a little bit taller. That's maximum likelihood's theme song. Log likelihood is a measure of height. It is the height of the data given the model parameters in a multidimensional space where each person gets a height, and the job of the estimator is to maximize the combined height. So find the parameters that make all the data as tall as possible. So it's a measure of goodness. And the saturated model, H1, tells us how high it could possibly be, and everything is relative to that as worse or not worse. And so we have a saturated model in CFA because we have a covariance matrix. We have a saturated model in IFA under WLSMV because we have a polychoric correlation matrix. We do not have that under full information, maximum likelihood, and IRT, which is trying to reproduce all the response patterns for which there is no saturated model because we don't have enough people to fill them all out. So, all right. Does that answer your question, Andrea? Yeah, good. Okay, other questions on this? Okay, let me know if any come up. I'm happy to clarify. I'm happy to let you walk through the logic, and I can either confirm or deny that your logic is correct. That's what I can do. So if it helps to talk these things through, I'm happy to do that with you. All right, then we got some new stuff for today. We got a rock, we got path analysis and SEM. So one of you sent me an email asking if I was going to offer any more classes on SEM because I'm not talking very much about SEM this semester. And so the answer to that is maybe. In a one semester class, you have to make choices about what to include and what not to include. Every class is like that. And I deliberately made the decision to spend the bulk of our time on measurement models because I thought it would be disingenuous to talk about CFA and SEM and then tell you at the end, oh, by the way, you all have ordinal data. None of this is appropriate for you. Good luck. Which is the typical SEM class spends their time that way. And so I chose to lump in link functions and other types of measurement models because I wanted to show you that no matter what kind of measured data you have, you can fit a latent trait model to it. And so that came at the cost of spending time on what people would consider SEM, which is looking at relationships between your factors. So how your factor predicts something else, how it is predicted by other things. But I gotta tell you, this is the easy part. I don't know what else I would have said because once you know how to make a measurement model, once you know how to test factor structures, it is much, much simpler from that point just to see if there's a regression path that goes to your factor and if it's significant, because that is exactly what you learned how to do in your very first regression general linear model course. It's all the same from that point forward. And it's much harder to screw up a structural model because there's fewer things in it. Like you can leave out paths, but it's obvious that you've chosen to do that. A lot of structural models are saturated. They have all possible paths and they're looking at unique effects of things. And so there's no way to be wrong. So part of my rationale is because, yeah, you're going to see it's really straightforward from here on out. The other part is that it's hard to come up with distinct examples that would work for everybody. And so one of the things that I thought about doing in the future, if I have sufficient degrees of freedom, would be to offer an advanced version of an SEM, but make it like a project-based course, kind of like a guided, not independent study, where people who would enroll would come with a particular type of problem, and that would be sort of a project that you would work on throughout the semester. And that way I could tailor what we talk about to whatever particulars that you would have in your data. Can I just get a quick survey if anyone would be interested someday in attending a class like that? Like an advanced SEM sort of come and play kind of thing? At least a few people. Yeah, I wish that this could be a 2 semester sequence. Like I think that this material there's enough material here to go like that spreads into 2 semesters easily, and then I can add more SEM stuff. But until that happens, I have to try and figure out how to make it fit. So that was one idea that I had as sort of an advanced practicum where you could come and fit models. They could be multi-level models, they could be structural equation models, they could be combinations, something like that. So maybe in the future, we'll see. It depends on, it is a degrees of freedom problem. It's like who's teaching what and what else needs to be covered, and then do I have room to be able to work this in? So we'll see. But it is SEM. You kind of, it's like Dorothy in the Wizard of Oz, and you pull back the curtain, and it's like, oh, you had the power all along, right? Like that's what this is going to look like. Like, oh shit, I know how to do SEM. I got this. You need to learn one new word to do SEM. Do you know what that word is? On. O-N. That's it. Mplus code is going to have the word on in it because you're going to regress y on x. That's it. So we'll see an example, and hopefully you'll see that this is a more straightforward process than what you may have imagined. If time is permitting, I don't know if I'll get a chance to cover this in class, but if I don't, then I'll make another video of it, is what not to do if SEM breaks. So there are compromises that people have used, and I want to discuss the pros and cons of various compromises and how people treat latent variables versus observed variables. So we'll see if we can get to that this week. So away we go then. Path models, just to get the language of putting in structural type relationships with observed variables first, and a few of the caveats with respect to that, and then adding in the latent variable component to it. So terminology. Yeah, go
Sorry,
ahead.
Lisa.
Sure.
Actually, I dropped I cannot find any PPT, so
It should be on the website. Let me see if I have if I can show you where it is, and if the link is broken, then I can fix it so that you all can have this. There is no link. Well, holy crap. Hang on. Let me fix it. Yeah, spoiler alert, guys. I'm not perfect. I screwed up. I hid it from you this whole semester of perfection until now. By the way, you are 2 people away from getting an extra credit point for completing your class evaluations. So the university evaluations close at the end of this week. If I get at least 23 of you to complete it, I give everybody a point extra credit. If you complete the separate Qualtrics evaluation, I give you a point of extra credit directly for that. So just as a reminder, let me fix the website real quick. Thank you for pointing that out. I would have felt really stupid if I had gone through this whole thing and nobody could actually follow what I was doing. 1 second. I think I was so relieved to have actually finished this last lecture that I just forgot to put it up. I'm like, oh, I'm done with it. It's done now. 1 second. And I'm going to hit refresh. There it is. Ta-da. Now you have my slides. Apologize for that, but thank you for letting me know. Okay. We got them? All
At
right.
least there are slides. In my nightmare, it'd be like, I forgot to make the slides. You're at the class about to teach.
Yeah, that could be fun. I'll just make shit up, right? Just really off the cuff. All right, here we go. So terminology is what I was going to talk about. So path analysis or path modeling, those are synonyms. That is just regression. That is describing relationships amongst observed variables only. The catch is that in path models, any one observed variable is allowed to be both a predictor and an outcome simultaneously. So I could have X predict W, and W in turn could predict Y. So the fact that W is both an outcome of X and a predictor of Y at the same time is why you would do path models. I teach path modeling as part of an earlier course because it really has nothing to do with SEM. It uses the same software, but the modeling and the logic of it is an observed variable technique. There's a lot of confusion about what kind of variables you can use in path models, and part of this is due to differences in what was available in software. So there are a number of structural equation modeling books and path model books that say things like all variables are assumed to be normally distributed. They have to be. The reason they say that is because once upon a time, The only software that you could use to fit these models only had multivariate normal as an option. And so therefore, if you wanted to fit these models, you had to pretend everything was normal. That is still the case in some packages. For instance, SAS has a routine called Calis, which does not have any link functions. So if you're going to use SAS Calis, everything has to be normal. Stata has an SEM package that is separate from its GSEM package. The latter has options for not normal. Mplus has a bunch of options for not normal. Lavon, I think the only kind of not normal you can have is categorical, binary or ordinal. Correct me if I'm wrong about that. Amos, does anyone here use Amos still? Was that a thing? It's SPSS's SEM package. That's one of the first ones I learned how to use. The last I checked, it didn't have any link functions either. I think everything has to be normal in that land. And EQS, which I'm not even sure is a thing anymore, that's the first package I learned. Last I checked, didn't have link functions. So it depends on the package. So if you see this language, everything has to be normal, just know that it's conditional on what you're asking the package to do. So I have examples of normal outcomes in those packages that have that. Software that allows you to have not normal outcomes. So by that I mean link functions and alternative conditional distributions. So for instance, if it's not normal, what is it? Well, if you're predicting an outcome that's binary, it's using a Bernoulli distribution instead of a normal distribution. If you're predicting an outcome that's ordinal or nominal, it's using a multinomial conditional distribution. If you were to predict, say, a count outcome, you could use something in the Poisson family. So there's all kinds of distributions that go with an alternative, not normal data, and they all require some kind of link function to make sure that the predicted outcomes stay within the boundaries. So stay within 0 and 1, for instance, in the binary case. So you just have to pay attention to what options are in your software to know how to be able to specify your model correctly. So path models are often described using pictures, which is great. Less often described using equations, and so I want to try and link these together. You already know this, the conventions. Boxes are things that are for real. Circles are things that are pretend. And by pretend, I mean estimated by the model as a latent variable or as an error term. You can think of errors as unobserved pretend things because they don't exist until you fit a model to them. If you have a two-headed arrow, like the one here on slide 3, that's a covariance. So it's an undirected relationship, whereas an arrow that has one side be the arrow is a directed relationship. So X in this picture is a predictor of Y. So the equation that goes with the picture would look like this, where I'm using superscripts to denote which outcome is being predicted, and the subscripts say what the predictor is. So this is one way to represent a complex system of equations. There's many other ways. You just have to make sure that you're internally consistent. And to be honest, when I'm working with these sorts of models, I always start with a picture. Even if it's not a nice picture, even if it's just like a scratch pad, I write out the picture of what I'm trying to do, and then I write the code from the picture, and then I write the equation from the code. Like that's the way that it goes in my mind. You will often see these sorts of models expressed in a matrix formulation because it's very compact, but it does very little to describe what's actually in the model, which paths are there, which way it goes, and so I find that less than helpful. But this is one example of a path model that would use observed variables. So I would call this a multivariate regression because y1 is being predicted at the same time as y2, and we have two different predictors of each. So when would you do something like this? Well, if you're interested in testing whether or not the effects on these outcomes are the same, so does x1 predict y1 differently than x1 predicts y2? If you have a question like that, the only way you can answer that question is to have both y1 and y2 in the model as outcomes. So this may be true if these are different measures. Let's say that you have two different ways of indexing depression and you want to know if your predictor relates to one way differently than another. This could also happen for repeated measures data, where y1 is an outcome under one condition and y2 is the same outcome under a different condition. So there's lots of instances like this. This type of formulation in particular, do any of you do dyadic data? Like people who are in families or relationships? Okay, well there's a particular type of model called the actor-partner model. That's this. So if I had, say, two people in a relationship and I have person one and person two, this this type of picture, the paths going from x1 to y1 would be the actor effects, like my x on my y and your x on your y, and then the cross paths in the middle are what's known as partner effects, my x on your y and your x on my y. So dyadic data can be fit with path models quite readily. And this is what the code would look like. So here's your new word for today, on. Do you all see that? So the way that regressions are specified in Mplus is y on x. And that's the way people talk about it. Y is being regressed on x. I hate that language. Like to me, it's like I'm not sure which goes which way just from that because I think of x predicts y. The only way that I get this right is if in my head, instead of typing on, I type an equal sign. It's like you're writing out the equation. Y equals this x, that x, that x. That's the way that this order is. And so this one line right here is specifying 4 different regressions simultaneously. It's x1 predicting y1, x1 predicting y2, x2 predicting y1, x2 predicting y2. So it's a very compact way. You can have as many effects on the y side as you want or on the x side. So you could write out all 4 lines if you wanted to, or you could abbreviate with this sort of listing them in bulk. The with statement you're already familiar with. This model says that whatever is left over in y1 after controlling for the x's is correlated with whatever's left over in y2. And that's appropriate if you think about the fact that these outcomes came from the same person, so they're probably going to be related to each other. So just like we had in SEM, you will have an unstandardized solution and a standardized solution. The unstandardized solution recreates the original means, variances, and covariances. It's in a regression type of language, so a change in y for a 1 unit change in x. Standardized solution is if you had z-scored every variable in the model, changed its scaling so that 0 was the mean and standard deviation is 1. The standardized coefficients then are all in a correlation metric. So in talking about the effects of one variable predicting another, it's often very convenient to report the standardized solution in the picture. That way people can talk about it in a regression sort of standardized slopes kind of way. So covariances become correlations, regression slopes become in a correlation standardized metric for this. Okay, here's some words that get confusing in this language. The terms exogenous and endogenous. So exogenous is used to refer to predictors. The shortcut that I have is they're x variables, exogenous, because x's are always predictors in my equations. Endogenous refers to outcomes, and so I think of them as endogenous. Like if you look at this picture and there's arrows going into something, it is endogenous. It works. So in this picture, I would say there's 2 exogenous variables, x1 and x2, what used to be called predictors last week. And then there are 2 endogenous variables, what used to be called outcomes. And this blue part here is showing 2 different ways of representing the idea that an endogenous outcome has residual variance. You can either make a curved arrow into itself, and people call that variance, or you can make it explicit and show E as another predictor that's latent of this. And so like y1 is partly whatever x1 contributes, whatever x2 contributes, and then whatever's left is E. And so this circle is what we've been using in the SEM diagrams to convey residual variance. You may also see it written this way down here. Question. So when people complain about endogeneity, that's like a 3-beer question. Endogeneity is a whole thing in certain fields, and I had never come into contact with it until after I started teaching people from those fields. Yeah, sociology, political science. There's certain fields that have like endogeneity problems. It sometimes refers to not having correlations. It sometimes refers to, in a multi-level modeling context, when level 1 predictors are correlated with level 2 outcomes, and the only way that can happen is if you set up your model wrong. So I'd have to see like the particular endogeneity complaint to see exactly what they were talking like. Omitted variables, yeah, that's usually sort of the language where there's things are correlated when they're not supposed to be, is the endogeneity problem, but there's also language associated with it that talks about sort of, can you really say that this is a predictor of Y, or could it be the other way around? I've also heard that kind of language used with endogeneity. So eh, I'm just going to be like, I don't know this, because I'd have to see the particular context in which the word was used to figure out what they meant by endogeneity in that case. So I'm going to call an audible or punt or whatever sports metaphor works for this situation. So this picture then, we could also have a picture that looks like this. Yeah, you'll have to define it in your job talk, but not for today. The only difference is right here where I have Y1 predicting Y2. And so this lower picture is an example of a model that you could not fit in a regular regression software like ProcGLM or ProcMixed or Regress and Stata or whatever, LM and R. Anytime you have a variable that is both an outcome of something and a predictor of something else at the same time, that's what path models are designed for. You would have to do it as separate models and somehow combine the results back together if you're using standard GLM software. So this is really the situation in which this is is most advantageous. And so this model then would be expressed in Mplus as the box down below, where I replace the width that used to be here with a Y2 on Y1. Is this where the term recursive and non-recursive comes in? Oh boy. I didn't know I would be like on a quiz show today. I'm giving you shit. I'm just kidding. Okay, I know recursive and non-recursive is the opposite of what you would think it is. So I believe this is non-recursive. One of them means, so they're used to distinguish models in which arrows go both ways at the same time versus models in which they don't. So like if you have a model that's like X predicts Y and Y predicts X, like the arrows go both ways. One of those words refers to that situation, and I can never remember which one it is because I've never developed an effective mnemonic. If someone would like to get on the Google and search for a picture of non-recursive versus recursive, you can help me remember which it is. When I see models like that where the same covariance is trying to be split into two parameters, I just think unidentified and I move on. Because even though if you can trick the model into estimating it, it's silly. Like X and Y are correlated, the end. Like there's no way with just two variables to pull apart how much of it is the first arrow versus the second. We have a recursive model is where all causal directs are unidirectional. Okay, this is recursive then, I think. Everything is going one way. There's no feedback of like Y2 going back to X1 or any of that. Okay, thank you. I just learned something today. This is recursive. Also, this works. All right, now where it gets confusing is what properties of the endogenous versus exogenous variables count. So here is the thing. In Mplus, there are two different kinds of predictors that are possible. There are what I think of as predictors, which are not in the likelihood, the same as in regression. They don't have distributional assumptions, they're not in the likelihood, they just contribute to the predicted outcome and that's it. In those cases, you cannot have missing data. If you have missing data on a predictor, that is not in the likelihood, that case gets deleted. The same thing as what happens in regression, because you can't compute the likelihood if you don't know what the predicted outcome is. And so if you don't know what the predicted outcome is because you don't have the predictor, it can't be done. And this is bad from the perspective of missing data, but it's also good from the perspective of that means we can have whatever kind of predictor we want. So if you think about analysis of variance, remember that back when life was simple and we didn't have any circles? What kind of predictors are in an analysis of variance model? Those of you who've had me before, you better get this question right. We've talked about this. Observed predictors, that is true. All of the general linear model concerns observed variables. What kind of predictors are in ANOVA? Categorical, there we go. I knew you knew this one. Yeah, ANOVA is all about mean differences across levels of a categorical predictor in a quantitative outcome. So could you do ANOVA if I told you that all variables had to be multivariate normal? Well, no, because the predictor's not normal, so does that mean game over? Well, no. So from that perspective, like, well, this is fine. You have a predictor. It could be whatever it needs to be, just like normal, even if it's not normal, and it just you can't have missing data on it. And this is the point when I tell people this, that someone raises their hand and says, no, but I thought SEM handled missing data. Because handled is what you say when you don't know what you're talking about. It is this like a worse, nice, like multi-level models handle dependency. Structural equation models handle missing data. How? They handle it. It's fine. It's do any of you watch the show Schitt's Creek? It got like, 17 Emmys this year or whatever it was. A great show, right?
Show.
It is a great show. It took me a while to sort of get into it, but then we got into it and I liked it. But there's an episode where they're trying to cook in Jocelyn's kitchen, and the recipe book says you fold it in. You're supposed to add cheese to the recipe and you fold it in, and they go back and forth like, how? Fold it in how? Just fold it. Just fold it in. And like there's neither of them know what the hell fold it in means, right? Yeah, does anyone know what that means? Do any of you cook? What does it mean to fold in an ingredient? Oh, I'm getting gestures. Would you like to clarify? Stir it in slowly?
Well, when I've seen it done in videos, they have to take their spatula, scoop it under the dough, and like put your whatever you're folding in, and just like do this gesture.
Okay, so kind of like stirring, but lumping over.
But you're folding.
You're full, but it's not cloven. Like it's food. Okay, that makes a little more sense. So it was a great like skit where neither of them knows what folding is and they're trying to figure it out. Thank you. We have a link in the chat window to educate yourself. The handle is like that. Like it handles it. How? It just does. Okay, just fold it. All right. You can have missing data because everyone says SEM handles missing data. So I want you to know the answer to that question. How does missing data get handled? Well, it makes it so that what you're calling a predictor is an outcome. That's how. And so in Mplus, you get a choice in the matter. In other programs, you don't. And so I have a few slides about that for those who use other programs. What happens in Mplus is that you can trick the model. If you take a predictor and you list its mean, its variance, or its covariance with something else, Mplus is like, oh, it's a Y. It's an outcome. Got it. Okay. Into the likelihood you go. And then the same rules about finding a multivariate likelihood if there's missing data. The assumption is that the multivariate shape would be the same if you had complete data, that you're not coming to a different answer, but that you don't necessarily have to have every complete data point because you can get a likelihood of what's left. And so Mplus is like, cool, got that. But if it's an outcome, then it has distributional assumptions. So then you're in a quandary. How much of a problem is it if those assumptions aren't met, if you're relying on that trick to be able to include cases that have missing data? And so this is a topic that I'm interested in finding more about, hint, hint. And that's one question that I don't know the answer to. So Mplus is one of the programs that I know that offers you a choice. You can have a predictor that's just a predictor. If you do that, it can't have missing data, but it has no distribution associated with it. If you bring it into the likelihood, then it's missing at random, but you have to have a distribution for it, and you can be wrong. So what happens in other programs here, I have a description of the bottom line here is that you got to read the documentation to find out what it's doing, and it's actually somewhat hard to figure that out, even for me. So here's my reconciliation of all of this confusing terminology. Is your variable in the likelihood? Then it's an outcome. Then it's endogenous, even if nothing is predicting it. If it's not in the likelihood, it's a predictor. So missing data is only handled to the extent that you're willing to turn all of your variables into outcomes. Otherwise, cases with missing data are kicked out if they're just predictors. So that means you have to reconfigure your model and have a predictor become predicted, or you have to just list its mean, variance, or covariance. So I use this trick in one of the path models I sent a link to. I think it was example 6A from my previous class to get around missing data in an X variable. I used this trick in example 6B for an outcome that had some missing data. We'll talk about that in the context of this example, but just know that it's not a panacea. You can have missing data on a predictor if you're willing to treat it as an outcome. And so this endogenous versus exogenous thing gets very murky as to what something's doing. Just pay attention to whether or not its parameters are showing up on your output. If they are, it's in the likelihood. All right. Questions, comments, thoughts? I am very confused. So am I. Can you make it an outcome without actually putting in predictors? Yes, you can. From an estimation point of view, you are taking the properties, the summary statistics of that variable, its mean, its variance, and its covariance, and making them things that the model has to find, making them things that the likelihood is trying to iteratively solve to figure out what value makes the data the highest. That's what it means. How would I write that up? Oh, great question. Let's say, let me like call on Job Talk Lisa, like not the Lisa that talks about Schitt's Creek. I gotta like dive back in here. How would I write this up? Predictor variables were brought into the likelihood function in order to include cases with missing values under an assumption of conditional random missingness, e.g. or i.e. missing at random. How's that? That sound like vague enough? I think see example syntax in the online appendix. There you go. And then if somebody understands what the hell that sentence means because they saw your Mplus code, then it's like, we followed the approach of Hoffman et al. To bring our predictors into the likelihood. Because if you provide syntax, then all of a sudden it's your approach. I'm sort of being facetious, but I'm sort of not. I have a paper that I published in 2007 that took code that I found in the SAS Mixed Models book. So a book that had been published like 10 years previous, and I applied it to a particular problem that I had never seen used that type of method before. And then whenever people cite that paper since then, I am credited with developing that method. I'm serious. I'm like, and it's funny because I get asked to review those papers, and then I have to tell the authors, actually, no, Hoffman 2007 did not develop that method. She stole it from the SAS Mixed Models book. Not that I would know as the anonymous reviewer. Yeah, true story. All right, so it's almost like an empty model of sorts. Yes, yes, that's exactly how I would describe it. If you have a variable that you are using as a predictor, but you are bringing it into the likelihood, then you are estimating a mean for it, it's variance because it's not leftover because it's not being predicted, and potentially it's covariance with other variables that are in the model. So it's like you're fitting an empty model for it. Yes, that is a great way to describe it. Okay, other questions? A lot of vocabulary with this, isn't it? It's a lot of words. But here's some words you know. Identification. You know that word, right? Whether or not it's solvable mathematically, identified. Here is how you come up with degrees of freedom. You guys already know how to do that. There's only one catch, and it's what do I do with the predictors? So that is the part that gets a little bit screwy, is predictor variables count in degrees of freedom sometimes, but not always. So if we have, let's see here, what's going in for a variable? If a variable is in the likelihood, its mean is going to become an intercept. Its variance is going to become a residual variance. How those get labeled on the output depends on whether or not it's actually being predicted. So if you have a predictor that's in the model, but it's not predicted by anything, its intercept is going to be called a mean, and its residual variance is going to be called a variance. If it is predicted by something, then it's an intercept and a residual variance. So they'll be in different places in the output based on whether or not it's a predictor or an outcome for real. And because each variable gets its own mean or intercept and its own variance or residual variance, these won't be the cause of any misfit. It boils down to covariances. So if you have a covariance between pairs of outcomes, you can reproduce that with a regression path, so an on, or a covariance between the residuals for that outcome, and it will be perfect. If you have a covariance of a predictor with each outcome, you can replace that with a path or a residual covariance, and it will be perfect. Whether it's covariance depends on whether or not the variables of our outcomes are predictors. If it's predictors, it's covariance. If it's outcomes, it's residual covariance. So it's the same language we've been using to talk about outcomes, just with a twist when it's a predictor. If you don't have all possible direct paths between a pair of variables, that's where misfit creeps in. So every pair of variables needs to have either an arrow connecting one to the other or a curvy arrow, a covariance. Otherwise, there's the potential for it to be incorrect. So two things to know: is the model estimable? Can you actually solve it? And then is it testable? And we've already talked about all of these situations: under-identified, just identified, or over-identified. So here's some pictures using just observed variables. Each of these pictures is going to fit equivalently. So despite the fact that the arrows go different ways, whether I have X as a predictor of Y as a predictor of Y2, or whether I just have these three variables get to be correlated, or I have Y as a predictor of X, model don't care. These will fit equivalently. And these are each over-identified because there's 1 degree of freedom, because none of these models has a direct relationship between X1 and Y2. So each of these models is saying that the covariance between X1 and Y2 can be recreated by tracing through these paths. So the model says right here, this path times that path is the relationship between X1 and Y1. And this does the same, but in the opposite direction. There was a mnemonic one of the students last spring developed for over-identified. If one of the paths has been overlooked, I thought that was good. If you've overlooked one of the paths, then it's over-identified. So the double arrow doesn't change anything. Nope. Double arrow gives the direct relationship between X1 and Y1, but you could get from X1 to Y2 by going across. So yeah, they all will fit the same. This is a just identified model. So now all possible relationships between the three variables are in here. So I've taken 3 covariances and I've expressed them as a combination of regressions or covariances. And then this one, This is non-recursive. Hooray! I think I got that one right. So that doesn't work. That's an example of under-identified here. You only have one covariance between these variables. You cannot tell how much of it is because of one causing one and the other causing the previous. So the only way that you could possibly tease apart two different parts of the same relationship is using external information. You'd have to have other stuff in here to identify the model, but conceptually it doesn't make sense. There's only one relationship here. So here's some examples of more elaborate path models. So this is one where I have variables A, B, C, D, and E. A, B, and C are my predictors. D is an outcome of A and B. E is an outcome of C. D is both a predictor of E and an outcome of A and B, and F is only an outcome. So to set up this model, this is what the code would look like. I have Y on these two X's, so D on AB, E on DC, so here's E predicted by D and C, and then F on E. So is this under-identified, just identified, or over-identified? What do you think? One vote for over? Yeah, are there paths missing? That's the question. If there's paths missing, then it's over. So the degrees of freedom for this model would be the number of direct paths that could have been included that weren't. So for instance, there's nothing directly connecting C and D. There's nothing directly connecting B and E, B and F, A and E, A and F. So all the things that are missing are potential sources of misfit. So this is over-identified. Things that are going to be estimated that you don't have to type. Each variable that is downstream, that is an outcome, that is in the likelihood, gets an intercept. So that's the terms in brackets, and it also gets a residual variance. So that's the same as what we've been seeing. To bring A, B, and C into the likelihood. So to allow cases that have missing data to remain in the model on A, B, and C, you would list one or both of these statements. You would estimate the covariance among A, B, and C, or the mean for each variable and the variance for each variable. That's what I mean by bringing it into the likelihood, those bottom two sections. Otherwise, those are not model parameters. So think about this in the context of just regular old regression output. Do you remember that? With observed variables, and there's like only one Y and there's some X's. What you get on your output from a regression model, you get the intercept for Y, you get the residual variance for Y, and you get how each X predicts Y. You don't get any information about your X's though. You don't get the mean of X, you don't get the variance of X, you don't get the covariances because you don't need any of that. Those are extra things. The fact that these paths are controlling for the other predictors sort of means that the covariances are being taken into account in finding what those paths are, but the covariances are not estimated directly. So these things would not be model parameters unless you asked for them. And the reason that you would ask for them, A, B, and C, as means, variances, and covariances for those variables is to be able to have missing data on them. Question, do we estimate I to D, J to E, K to F? No. So this I, J, and K are the residual terms of the outcomes. So it's another way of saying that these are E variables that are going into each one. So I is how much of D is not due to A and B. J is how much of E is not due to D and C, and so forth. Yep, yet another residual convention, how to express that. All right. So in terms of how to figure out what the model says these relationships are, there's something called Wright's rules of tracing. So you can go forwards, but you can't go forwards and backwards. You can't have loops that pass through the same variable twice. And you can only follow one covariance. So for instance, if I want to say, what is the model implied relationship between B and D? Here is part of it. So this path right here that's labeled lowercase b, that is part of the model implied relationship between B and D. But the other part of it is given by going from B over to A and then down to D. So the lowercase b that's labeling that path is conveying the unique effect of B in predicting D. But there's another effect that is implied by A. So the total effect is the sum of these two unique effects. A and B, I can't find the model implied relationship going from A to B by going down to D and then back to B. So you can't go downstream to an outcome and then go backwards along the arrow. That doesn't work. If I want to go C to D, then I can go over to B and then down to D. Or I can go from C over to A and then go down to D. But I can't go from, let's see, C, I can't go down to E and then come back up. So it can get very tricky to figure out how the model predicts relationships. But the bottom line here is that if you don't have a direct relationship between a pair of variables, either single-headed arrow or double-headed arrow, if you don't have a direct relationship between a pair, you have the chance to be wrong. If you do have the direct relationship between a pair of variables, you will not be wrong. And you can ask the software to come up with the model predicted covariance matrix and to compare it with the real one to see how far off you are. And you already know how to do that. We called that local fit. It's the same premise. All right, and so then this describes in the unstandardized metric how you would go about this process. And here's some more math for you. So this is how you can talk about recreating variances and covariances as opposed to just correlations. And so there are rules about when a model is identified versus not identified. And they're very complicated rules, and I'm telling you, I wouldn't bother learning them. I can tell you by looking at a picture whether the model is identified, whether or not the same relationship is in there twice. If it is, it's not going to work. So for instance, if I had y1 predicting y2, but then y2 was also covaried back with y1, that won't work. So long as you only specify each pair of relationships with one thing, you should be fine. All right, so we would go through the regular process of looking at absolute fit, local fit, adjust the model until needed, as well as paying attention to effect size. So one of the more common questions I get from people doing path models goes something like this. They show me an output where none of the paths are significant. And then they tell me, but the model fit was almost perfect. How can I have perfect model fit but nothing significant? What's my answer? How can I have perfect model fit but have no significant paths? I'll wait. I know you know this, or at least I hope you do. How can I have a perfectly fitting path model, or nearly perfectly fitting, that has no significant paths? Because it can happen. A perfectly wrong model? Wrong how would be my question to that. What does fit refer to? If a model fits, what does that mean? Theoretically wrong? Could be, but the fit statistics can't tell me if my theory sucks.
Would I be right in saying the fit is how well the model, how your idea of how the different variables are related to each other is like accurately representing the way that the variables are relating to each other? But
Yes.
if it's not significant, then that means that they're just, like you were right, that they're not that, how they're related, but they're just not that related. Like
Mhm.
that those predictors just don't significantly predict the outcomes the way you
Yeah,
might have been hoping.
yeah, your model has accurately captured the lack of relationships between your variables. That's what it means. So if they're not related to each other, then that's what the paths are indicating. The fact that you have accurately reproduced those non-relationships is why your model fits well. So this is why fit is not the same thing as effect size. Effect size would be how strong are these relationships? Are they worth reproducing in the first place? So this is commonly misunderstood. Fit is not effect size. Effect size would be how much variance was accounted for in Y1 by these predictors. That kind of thing. So path models are often just identified or very close to it. That way you can look at all possible combinations of how predictors relate to outcomes. They will fit well. The question is, what relationships have you captured with your paths? That's a separate question.
I guess I was going to say the same thing, that, well, maybe it just means that it's not, whatever your factors are and your items are just not predicting what they're supposed to be predicting. But I don't think I understand the model fitting well part, because I would think that it would fit well if they are related. But how can you have, I don't know how it makes sense in my head.
So the goal of the model is to reproduce whatever correlations are there between your variables.
So it would be like a negative correlation
Could be.
then? No, if they're not related, then there would be just like a zero correlation.
A zero correlation, yeah. So at the extreme, if you had 4 variables that were completely unrelated to each other, the model could accurately capture that by estimating paths that were 0 or covariances that were 0, or leaving them out, actually.
Okay.
If there were no relationships, the null model would fit. The null model in which each variable gets a mean and a variance and there's no covariances, that could fit perfectly if the variables are unrelated.
Okay.
So this would manifest itself in factor loadings that are close to 0 in a CFA or IFA context. You could have a latent factor that fits well, that captures very little of the variance of an observed indicator. That would be the analog to this situation.
I have a practical question that addresses this.
Mhm.
So like I'm thinking about my own factor structure, and like I had a factor loading that was really low, and I know that that's not an example of model fit, but when I take it out, the model does fit better. So I realize that that's like confounding both of these things at once, but I guess the way that I am explaining that to myself in my head, hopefully this makes sense. Tell me if this is right. Is that the it made more sense just to not account for the variable at all than it did to account for it with a small amount of loading. And that's why it fit better without it, even though the loading was so small.
I
Is that
think
true?
it's close. So it fit better without it because the variable's relationships with the other indicators were not being
Mm.
reproduced well.
Okay. Which I could say the covariance with the other
Yes.
indicators.
Yes.
Okay.
Yeah, so the role of the factor loading would be to help predict why that indicator is related to other indicators. And so if the factor loading is very small, then that's predicting very little relationship with the other indicators. It could be related to some and not others, and that would show up as misfit. So if you kicked it out of the model entirely, then any of those mispredictions go with it, and the model could fit better. I would say that the reason to kick it out is because it doesn't measure your factor.
Right.
like game over for it if it doesn't relate to the factor. But you wouldn't be able to compare the fit with and without it because those are different answer key saturated models in terms of what the highest H1 would be. So that's just be careful with your wording and thinking about fit better,
Mm.
like it fits good or it doesn't fit good.
Gotcha.
Yep. Yeah. So back into regression. Did you worry about model fit? Back when you learned regression, did you talk about CFI, TLI, RMSEA, any of those letters? Nope. Do you know why? How well does a regression model fit? Perfectly. Because all that's in it is the variable outcomes mean and its variance. And you got that. So fit is not relevant. What you worried about in regression was effect size. You worried about R square, you worried about the individual slopes of predictors and stuff like that. That's still true. So if someone brought me this model that has no significant relationships and they're like, but it fits, and be like, well, that's not worth keeping it. It's like if you have, you go to the dollar store and you're like, I found these pants and they're only $1, but they're hideous. Like, don't keep them. Like, just because you can have it doesn't mean it's worth anything. Fit is not the end of the story. So if it fits well, that's a precursor to examining the relationships. But if the relationships aren't there, then that's not anything different than usual. It means your story is this stuff isn't related. Which you could make that into a story, but that would be more challenging to argue that the null is interesting. All right, so we're out of time for today. We'll talk more next time about the transition from this into SEM, the magical on statement, where we'll use to describe relationships amongst our factors. So let me know if you need anything. Office hours start now. Otherwise, see you Thursday.